This is section 16.2 on the topic of line integrals, the last of these new types of integrals we're going to see this semester. Let's start out here just kind of looking at a broad overview of what we're going to do with line integrals, then we'll get into the details. Really, we're going to look at three new types of line integrals, all of them considered a type of line integral, but there's kind of three varieties we want to look at. All of them start with this basic assumption that you've got some curve C in the domain of either a function, scalar function f, that can be 2 or 3 variables, or some vector field, capital F, also could be in R2 or R3. So it turns out there's three different types of line integrals we're going to look at, all with this basic sort of setup that we've got some curve here in the domain of our scalar function or vector field. And we want to think about that thing as being represented by that curve C being represented by some vector function, R of t. Right? We've seen these before, but we're always going to think of these vector functions, R of t, describing these curves C. And so you want to think of these as having some x component function in terms of t, some y component function, and some z component function in terms of t. And we're saying we get a curve when we take that t value from some starting point A to some ending point B. So that's sort of the setup. We're thinking of having some curve in the domain. The idea is there are different ways that we can integrate over just a single contour, a curve in the domain, rather than a 2D region, a planar region, like we did with double integrals, or a 3D solid region, like we did with triple integrals. Now we want to integrate over just a contour through this domain. We're going to call that C and assume it's got some representation, some parameterization. That's what we call this. Of that curve C. That's what this R is going to be referred to. It's a parameterization of this curve C. So the three types of line integrals we want to look at, integrals over a curve C like this, are this first type where we take the integral over that curve of our function with respect to ds, line integral of f with respect to ds, which you'll remember from earlier on in the term. This is the differential of arc length. Right? That ds was the differential of arc length. So it's saying that at every, well, so let's just label that. This is called a line integral with respect to arc length. So we'll see what that means. That's a certain type of line integral. Another way we could actually do this integration is not with respect to arc length, but with respect to x, y, or z, any one of the variables in this domain space. This is, I'll just call this a line integral, exactly as it said it in words, with respect to, WRT for with respect to x, y, or z. Z. And now this last one's fundamentally different, right? Instead of having a scalar function f inside like we did for the line integrals with respect to arc length or with respect to x, y, or z, this last variety down here is a line integral of a vector field f dot dr, which might lead you to think the differential of this r parameterization. That's exactly what it is. We'll see this is another expression for this f dot t ds. This t is actually the unit tangent vector on this parameterization. So we want to review unit tangent vectors, these vector functions in space curves. But this, I will refer to as I'll refer to this as a work integral. And we'll see why I'm going to call it that. But it's fundamentally different than the others, right? We're integrating a vector field over the curve C rather than a scalar function over the curve C. You might say, well, this is just a ds integral, though, down here, because we do re-express it this way, where we have a ds of this dot product. A dot product's a scalar quantity, so this is a scalar function in here now with respect to arc length. So there is some connection between these two. And we'll see that there's really a nice connection between the x, y, and z line integrals and these f.dr work integrals. Okay, so let's start out though, start at the beginning here. Let's figure out what's going on with these arc length integrals, integrals with respect to arc length. So let's see it here. The idea is pretty simple, right? The idea is we have, maybe we think about this in 2D first. Yeah, let's think about this in 2D. It's going to apply just the same for 3D, function of 3 variables. It's just a little harder to draw that domain region, that curve C. So let's say for a function of 2 variables with the curve C in the xy plane, that's how I'm going to kind of demonstrate this. It's easier to draw that way. We're saying we have some function f. That guy's graph is in 3-dimensional space. It's a surface sitting above the domain. But I want to just sort of sketch this domain. We have some curve C that we want to integrate this function over. Every point on this curve is a point that you can plug into f. Well, so the idea to actually do this integration is exactly the same as it's been for every other type of new integration we've learned. We chop the region of integration, in this case the curve C, chop into a bunch of little pieces, sample the function value at some sample points we call xi star values, yi star values, that's our curve C to be clear. Right, so the idea is the same as always before. We want to take this thing we're going to say is going to be equal to, as a definition, whether we do 2 variables or 3 variables, I'm not going to be specific here. Let's just say this equals the limit as the number of pieces, say I chop this into n pieces, as the number n of pieces goes to infinity, of the sum over each one of those pieces of the function value at our sample point on any given piece. So the function value, I'll say evaluated at a sample point, the ith sample point, times this little amount of arc length, which we'll call delta Si, the ith one of those little arc lengths. These arc length, little pieces of arc length might differ, so I'm going to actually label this is the ith one. This is how we actually define this ds line integral. You could have 3 variables or 2 variables. That's why I didn't actually write f of xi star yi star, because maybe it's got a zi star in there too. This definition works for both 3D and 2D. Right, so let's actually scroll down and see that written out more nicely. Here we have, down at the bottom of the page here, oops. If f is defined on a smooth curve C, we're throwing in that extra little assumption that our curve's smooth, doesn't have any sharp spots anywhere. If we do that, then, and say C is defined by this R of t parameterization from t equals a to b, then the line integral of f along C with respect to arc length is, this is a definition for the 2D case, works just the same for a 3D case. It's this, oops, it's pretty terrible. It's this big expression. The limit of the sum of the sampling of our function on each little piece times the size of each little piece. That's the exact same procedure we always did when we were creating new types of integration. But you might remember we don't typically use this limit definition to integrate. So how are we going to calculate this? If we're not going to use the limit definition, how will we do this? We're going to do it kind of how we handled setting up iterated integrals for the double and triple integrals. We are just going to kind of follow our nose here. We want an integral here where we have our f of xy, but notice we want values of that when we're on the curve C, right? So let's say instead of f of xy, let's say this is x of t, y of t, where our vector function has those components. Or the parameterization of the curve has, messing that up. Let's see. That parameterization has x and y components, x of t and y of t. So we'll evaluate our function at the parameterization, then multiply by ds. Now what is ds? Remember, we actually saw this in the arc length section. ds is the magnitude of r prime of t dt. So we can just put that here. That's a nice little fact here. You might see that from this up here. Maybe you multiply the delta SI, multiply it and divide it by delta T. You have change in S over change in T times change in T. As we do take this limit as everything gets very small, this becomes the derivative of arc length with respect to T times dt. Derivative of S with respect to arc length. From here, we can see that's magnitude r prime of t dt. I divided over the dt. Right, so this delta s really gets replaced by the derivative of s with respect to t, which is magnitude r prime of t, times dt. So this is how we're actually going to operate, and now that we see this as an iterated integral in t, we better put t bounds here to stay on our curve. We know our curve starts at t equals a and ends at t equals b from this pretty standard setup of our parameterization r of t describing the curve. So this is a little bit of a mess. Let me see if I can clean it up a little bit. Sneak that in there, go around here. Alright, that's good enough. Maybe. Fixing this up here. There we go. There is my cat you might be hearing making noise there. Okay. Finally we have it. This is how we're actually going to set up these iterated integrals. We're going to see that the big trouble is finding this parameterization. You need those components of r of t to actually do this work. Right, so let's take a look. Before we get into examples of actually computing these things, how do we interpret what these line integrals are giving us? So let's look at this here. Given an integrable function f of x, so just a calc 1 easy function for x values between a and b, if we think about this little picture, the graph of our function, I'm thinking of it as the output being a z value instead of a y value. That value doesn't affect this, what we call that vertical value doesn't affect this area here, and that's really what I want to focus on. So we know that from calc 1 stuff, the area here is just the definite integral from a to b of f of x dx. So now what if we start thinking about this f of x function instead as a function of two variables, g of y equals f of x. Sure, it's independent of y, but we can say that when y is 0, so we're in the xz plane in 3D, this function is the exact same as g of xy. Where g of xy looks exactly the same as this little snapshot here in the xz plane. So I've kind of shown that here in our picture in 3D. This is my g of xy function looking just like my f of xy function from above, since these guys are equal when I look just above the x-axis, just at this picture. So I want to see, can we figure out if this curve if this curve down here, trying to make it bold, if that curve is the same as the curve above, here, then we should be able to figure out the area. And I just want to kind of cut to the punchline here that the area can be described as a line integral. The area is really just line integral along C of g of xy ds. This line integral, if I say C is this little interval along the x-axis from A to B, so the same interval that we integrated on up here, if I say C is that same interval from A to B as in the 2D picture above, but now we're seeing it as part of the xy plane, so we have to label it as some contour C in the xy plane, then this integral over that is the exact same. So that gives you a sense of what a line integral with respect to arc length does. I've kind of summed it up with a little note here. Integrating a positive function, meaning the curve isn't dipping, the function doesn't dip below down below the xy plane. If we integrate a positive function f of xy over a curve C in the xy plane, this gives the area below the graph of f, but just above that curve C. So this is kind of showing you that connection to Calc 1, but let's see that in more general terms. When our little interval that we integrate over in 2D isn't along the x-axis, isn't directly comparable to this Calc 1 situation up here. Well, in general, these curves C that we're integrating over for a function of two variables, they're in the domain, they're in the xy plane. So think of this solid curve C down here as being in the xy plane, lying flat. So it's got a parameterization of this form, two variables. That's all I need for the plane. Then we think of going vertically up from every point on that curve, going vertically up to the graph of our function f that we're integrating. So I would call this, I'm calling this in my picture C subscript f, meaning it's just the curve here, but projected upward to our graph, meaning all the points here are actually the points on C, but evaluated in our function to get their height. So in a case like that, this line integral over C of f, again assuming f is positive, this surface doesn't dip down below the xy plane, meaning this curve CF will stay above the xy plane, then this line integral actually gives us the area of a vertical curtain connecting this CF to this C curve down here. Let me see if I can try to shade that curtain in for you. It's this curtain. Right, all that stuff, all that area. Notice this is like a curvy sheet. It's vertical. It's got a lot of curvature to it though. That blue area that I've shaded, this wavy surface going in and out here and connecting up with the CF curve up here on the graph, the area of that is this integral's value. So somehow this is closely related to integrals we've seen before, still can be interpreted as an area. We actually don't typically use that interpretation too much, but it's nice to know. Finally, let's see an example of how to do some of these problems. We've talked the theory to death here. Let's go ahead and jump into a problem. This first one says evaluate this integral that I've labeled I, the line integral over C of 4 minus x squared ds. And so I'm saying this curve C is in the xy plane, so I'm viewing this as a function of, two variables. So we know how to set this up. The big key is that we need a vector function r of t that gives us this curve C that goes from 2, 0 around this circle of radius 2 back to 0, negative 2. And so you might remember that if I use in polar coordinates, it's pretty easy to express a circle. Or the xy coordinates on a circle of radius r. Right? The xy coordinates on a circle of radius r are just our cosine of whatever angle we're at times r sine of that angle, and y is r sine of that angle. So one way I could do this is say that all along my curve, we know the radius, the r value is 2. So let x equal 2 cosine of some number. It's going to represent this angle. Usually we use a t for this parameter, so I'm going to use cosine of t instead of theta. You could use theta. There's nothing wrong with that. I think this will just match our notation above a little better. But notice in all this stuff, we can see it now, we had to specify the values that our parameter t runs through to cover our entire curve. And we can see here, we do need to increase through these values. We'll kind of be integrating backwards there. But we could see pretty easily that the t values we should be trapped between, remembering t is like the angle we're at, should be 0 since we're starting on the x-axis, all the way up to 3 pi halves, the negative y-axis. 3 pi halves, positive 3 pi halves. So that's how we get this vector function, our r of t then, when we clear this out and write more space, r of t is just going to be these components. These components. Okay. And we've got this guy, the a and b value. So now to set up our integral, it's easy. We're going to take the integral, remember the form here that we're trying to match. Where is it? Up here. It's kind of a mess now after all my writing. Here's how we're using this. We put the a and the b, the endpoints of our parameter to cover our curve C. We put those on our integral. We take the function evaluated at the parameterization's x and y values. So f evaluated at the first component of r and the second component of r, times magnitude of r prime dt. So let's see what we get when we do that down here. Let's see what we get. Oops, jumped ahead. Here we go. Let's see what we get. So we need to go from a equals 0 to 3 pi halves. That's what we're integrating over. The function here is 4 minus x squared, so we need to plug in instead of x, we need a nice way to think about this. In fact, let me write this before we get into setting up the iterated integral. A nice way to write this is to say that this equals the integral from a to b of f evaluated at the parameterization r. That's just like our f of x of t, y of t. Just a compact notation for it that doesn't imply the dimension, so this works in 3D, whereas this formula kind of implies 2D. But now that we have it written in this vector form, it applies everywhere, 2D or 3D. This is very nice this way. So we'll take f evaluated at the parameterization. F is 4 minus x squared. Well, on our parameterization, x equals over here, 2 cosine t. So we'll put a 2 cosine t in for x. Right, that's our 4 minus x squared. And then we remember we need magnitude of r prime, so we go over here and we compute that. Pretty nice thing about parameterizing part of a circle with sine and cosine this way is that you can check it, this will work out, but this is always going to turn out to be the radius. The magnitude of r prime is always just the radius you attached. You can check this very easily. I'll let you check the details. Check that when you take r prime, get this vector, check that its magnitude is 2. I think it's pretty easy to check out. But so we get that this magnitude r prime of t is just 2. It doesn't have to be a constant. For some curves, it's not a constant. Here, it turned out nice, it was. And dt out of the end. From here, this is not so bad. I'm going to factor this 2 out to the front. Right now, this is nice. I have an iterated single variable integral now. This is nice and easy to compute. I'll just work through it. Factor that 4 out and put it with the 2. You're left with 1 minus cosine squared. That's just sine squared. And remember, to integrate sine squared, we want to use a power reduction formula. That power reduction formula is 1/2, so I'll just divide by 2 out front. Sine squared is 1/2, 1 minus cosine of 2t in this case, if I start out with angle t. Let's go and integrate here. Or anti-differentiate. 1 anti-differentiates to t. Negative cosine of 2t, I believe, makes minus, waiting for my eraser, minus 1/2 cosine of 2t dt. Okay, and we need that, not dt, we need that evaluated from 0 to 3 pi halves. Okay, from here it's pretty easy. I'll evaluate what I can, when I can. 4 out front. The t evaluated from 0 to 3 pi halves is 3 pi halves. That's from the t term, minus 1/2, but the sine term gives me a top and bottom. The sine term at the top is going to be 3 pi, sine of 3 pi, which is 0. And at the bottom it's 0. So all this is 0. So we get, looks like 6 pi. That's our answer. So if you could think of the graph of this function sitting over this xy plane, this surface, if I was just to take the vertical area upward from my curve C to that graph, all along this curve, it would add up to 6 pi square units. That's the idea. So you might be noticing we did make this little requirement in our definition of these FDS line integrals, that these would be smooth curves. It turns out if you have a piecewise smooth curve, so just some curve with a finite number of sharp points in it, you can integrate this just as well. The setup for this is think of each one of those smooth sections of your overall curve. Think of labeling them C1, C2, C3, out to however many you have. And think of your overall curve C as being the union of all those connected up together. Then it turns out we don't need to worry about this too much. You do exactly what you would think you can do. You can integrate to cover the whole curve C. You integrate over each smooth portion and add the results. And if you have more pieces, you could keep this going on and on and on. It's just saying a piecewise smooth curve isn't that big of a problem, but you do have to parameterize these pieces separately, typically, and integrate over each one separately. Okay, let's see an example using that idea. Here we have our curve C described by this curve C1, portion of the unit circle from 1, 0 to 0, 1. Then down the y-axis from 0, 1 to 0, negative 1. We're saying the overall curve C is both of those put together. And we're asked to evaluate the line integral over C of f ds, where f is a simple function, just equals x. Now we've already seen just what we were just now saying is that this is just going to be integration over one piece, C1, plus integration over the other piece, C2. So to do this, I just need to parameterize C1, and I need to parameterize C2 and get all those pieces that we need for these integrals. The magnitude of r prime, f evaluated at the parameterization, all these things. So let's see here, C1, this part of the unit circle here, again, maybe I'll call this R1. I'm going to use sine and cosine. Remember, you just want the radius, the coefficients on the sine and cosine to be the radius that you want to cover, so in this case 1. And this will be valid for t between 0 and pi halves, because those are the angles that this C1 curve covers, 0 up to pi halves. Well, you can compute this. Again, you can check this little trick here. The magnitude of the derivative is going to be 1 in this case, the radius of that circle we're covering with this r cosine, r sine sort of structure. Now we need to figure out how to parameterize this C2 curve that goes from up here to down here, or you can think of it as going from down here to up here. Notice arc length doesn't care which direction you traverse one of these curves in. Arc length is an absolute value, right? It's an actual length of curve that we cover. It doesn't care which direction we come from or where we're going. It's never going to spit out a negative value, for example. ds is always positive. So we can traverse this C2 in either direction. I think it is useful to start trying to get good at forcing a specific direction, because that's something we will try to do more in the next section. Is really force this parameterization to go from a specific starting point to a specific ending point. So now if I want to parameterize this, there's a pretty easy way to do this. Let's see what I can do. Well, all along this C2 curve, we know our x-coordinates are 0. Okay? And our y-coordinates just vary from a value of 1 down to -1. So you might say, well, okay, just let t equal my y-coordinate and say that t goes from -1 to 1. That works. The only issue with this is that this goes from the bottom point upward, which really doesn't matter for a ds integral. It doesn't matter which direction we traverse it. But just for a challenge, let's see if we can make it start up at the top and go down to here. Right, this starts at the bottom. When t is at its lowest value, we're here. When t is at its highest value, we're up here. So how can I force this to work in the opposite direction, start at the top of C2 and go to the bottom of it? Well, instead we could just try, I'll say or try, if we really do want to practice enforcing a specific orientation to these curves, just put -t here and say that goes from -1 to 1. Right? When I plug in t's lower bound, negative of -1 is +1 in my y value. I'm at the top now. When t goes to +1, well then negative of +1 puts me down here. So this thing traverses it nicely in this direction. We didn't have to do that. I just want to see how we do have control over such things for later cases where we do need to consider the direction we traverse curves in. So let's see here. Let's see if we can finish up this integration. I've got R2. Let me just make this little note over here. The magnitude of R2 prime. Maybe you can do that math. R2 prime is just 0, -1. That's a unit vector. So these are both pretty easy. I'm going to say that for the C1 integral, I'll take f, so this function, evaluated on C1, evaluated at cosine for my x and sine for my y. So f just turns into the x value of my parameterization, cosine t, times ds. Remember, that's the magnitude of r prime, that's 1 in this case. And we know this is going from 0 to pi halves. Our next piece goes from -1 to 1. It's this piece now. The function f evaluated at the parameterization, well, f equals x, right? On the parameterization, the x value is 0. So we get 0 ds. We don't even have to finish, that's 0. Integrate 0 on a finite interval, you get 0. So we're left just evaluating integral from 0 to pi halves of cosine t dt. Easy enough. What do we get? Sine of t from 0 to pi halves, which is 1. Check that work. So this line integral equals 1. Okay, let's move along here. Try another one. We've seen a lot about parameterizing portions of a circle using cosine and sine. This one, it's just another example of these line integrals with respect to arc length ds. But now our curve C looks like this little segment of a parabola that goes from the origin to 1, 1. So how do we want to parameterize this? This is actually pretty easy. If y equals f of x, a nice parameterization is just to let the x value be your parameter, and you know the y value in terms of the parameter, right? In terms of the x value. It's f of that x value. So it's f of that x value we chose. Right? So this is a pretty nice idea in general. If you do have a function, y equals a function of x, for your curve in the plane, just let your x be your parameter and let your y value be f of that parameter from wherever you start to finish, so 0 to 1 in our picture. So to be clear here, I'm going to do my x value, I'll just let be t, my y value is the x squared. That's what this is saying. And this is value valid from x equals 0 to x equals 1 to cover this whole curve. We know our x value is our t value. So now if we take the magnitude of the derivative here, that's our ds, remember we need that. That is the magnitude of 1 from the first component, not plus. Waiting on my eraser here. There we go. 1, 2t. If we take the root of the sum of the squares, that's 1 plus 4t squared. I shouldn't say ds just equals magnitude of r prime of t. It's really a differential in terms of another differential. ds is magnitude r prime of t dt. So I might have written that wrong up in the previous part. I don't think it makes too big of a difference. Okay, so let's continue on here. I think we've got all the parts. Let's just plug this in. From 0 to 1, we need x times y on this parameterization. X is t, y is t squared, so that's x times y on the parameterization. The ds, that's just magnitude r prime of t dt, which is the root of 1 plus 4t squared dt. Right, so what do we have? We're actually just trying to evaluate the integral from 0 to 1 of t cubed root 1 plus 4t squared. You might say, how do I integrate this? I don't have a nice single power of t outside the root to do a substitution. I'd say follow your nose and try a substitution anyway. And see what we get. When I plug in t equals 0, I get u as 1. When I plug in t equals 1, I get u as 5. So those are my new integral bounds after the substitution. And remember, this t I can break up as t squared times a copy of t. This is useful because I know t dt is really just 1/8 du. T dt is 1/8 du, so I can get rid of this t and dt. I canceled those, or I should say I replaced those with u expressions. Now what do we have left? Root of 1 plus 4t squared, that's just root of our u value. We've got this t squared left. That's not too bad. From here I can solve for t squared. What is it? It looks like 1/4 u minus 1. I believe that's t squared. Check me there. I think that's right. U minus 1, 1/4. Yeah, that works. And so we've completely replaced this for u expressions. Now we can simplify, bring the 4 and the 8 together. and rewrite this. Remember, u in a square root, it's just a half power, and I'll distribute that across the parentheses. And now we're good to go. From 1 to 5, I should say. Let's pick up over here. 1 over 32 times. I'm going to integrate. 3 halves becomes 5 halves power multiplied by the reciprocal of that. Similar over here. 1 half becomes 3 halves multiplied by the reciprocal of that, and 1 to 5, I should say. So it looks like we get, at the top value at 5, I get 2/5 of 5 to the 5 halves. That's a 5s and 2s in there. Minus 2/3 of 5 to the 3 halves. That's what I get at the top bound. At the bottom, I get, plugging in 1 into each of these, 2/5 minus 2/3. Feel free to fast forward a little bit. I'm just going to simplify this just to finish up. Group things so it looks easier to deal with. It's 2/3 times 1 minus 5 to the 3 halves. I think this is all accurate. Just boiling it down, seeing what I've got. I would even take 15 out of the bottom to make this. This. So it looks like we have 1 over 15 times 16 times this big mess. 3 times 5 to the 5 halves. Minus 3 plus 5 minus 5 times 5 to the 3 halves. Well, notice 5 times 5 to the 3 halves, that's just 5 to the 5 halves. So we've got 3 copies of that minus 1 copy of that. That's really 2 copies of that. And we've got negative 3 plus 5, that's plus 2. The 2 can factor out and cancel with the 16. What is that, 120? 15 times 8. And leaves behind 5 to the 3 halves plus 1. I don't think we can get much more reduced down than that. Okay, so long big mess past the real important part, the actual integration. But I hope we're seeing that the setup is definitely the hardest part of these. If you can come up with a parameterization R of t to describe the contour you're integrating over, the rest is really just following your nose. It's really not so bad. From having that parameterization, you can easily set up your iterated integral, which is a Calc 1 integral now. Pretty easy. So let's see another problem here that's sort of an application of these. You might ask, well, if we don't, if we have this area interpretation, what other sort of good ways to think about this line integral with respect to arc length might we have? So I think this example shows us one other application. If we consider a thin wire placed along this curve that I've labeled C, so it's along the unit circle outside the first quadrant, we say that thin wire has a linear density at any point in the wire given by the distance from the point to the origin. Using that information, let's find the mass of the wire, and then let's see if we can find the center of mass of the wire. So we haven't done stuff like this before, but we've talked about it briefly. We saw that for a solid region E, we saw that the mass of it was equal to the triple integral over that region of its density function. Right? That was a mass density. Well, now we're saying the mass of this curve, of this wire placed along curve C, should be a line integral over C of the same sort of thing, except now since it's not a volume that we have along this curve, it's just a linear curve. It's not a linear curve, it's a linear object, it's a one-dimensional object. In that case, we're not going to have a mass density in terms of like mass per volume. Instead, we're going to have a mass per length. So that when we multiply by ds, well, ds has units length, and we get the total mass, right? So it follows the same way. And also, we saw formulas for the center of mass of a solid object. We saw those were the x-coordinate of the center of mass is x times that density integrated over the region divided by the mass. Same for the y value and the z value. Or we saw these formulas, we didn't work out any examples with them. Well, we do the same sort of thing here. The coordinates of the center of mass of a wire with linear density rho. This is not the rho that we talked about in spherical coordinates. It's not the spherical radius. It's just an unfortunate coincidence our book uses this symbol rho for both density and that radial distance in spherical. So coordinates of the center of mass of a wire with linear density rho are, in 2D, it's x bar equals the line integral of x rho ds over the mass of the wire, and y coordinate, which we call y bar, y rho ds over the mass of the wire. Now, if there's a z coordinate, you do the same thing for z bar, but here this is a 2D wire. It's located in the plane. So we're just going to have an x and y coordinate of the center of mass. So with all this kind of setup, I think we can do the rest of this problem. Let's notice first of all that the mass is going to be pretty easy. I should back up, I do need to find a parameterization of this curve. That's easy. This is just part of a circle, a unit circle even. So use cosine and sine again. And in this case, it looks like those angles we'll go through are pi over 2 to 2 pi. Start here, go all the way around to here. Magnitude of r prime, we know that. It's just the radius, it's 1. And so this is easy. If I want to take the mass of this wire, we just integrate from starting point, from starting t value to ending t value. The density, ds. I'll write the ds part. It's 1 dt. Right? Because the magnitude of r prime is 1. But what is the density here? We're saying that the linear density, the linear density here is given by the distance at any point on this wire, is given by the distance, is given by the distance from whatever point we're looking at on the wire back to the origin. In this case, we can see it's going to be 1 for all of them. So in our case, nice enough, the density is a constant 1. In this case, we said kilograms per meter. So when we plug in the density function, it's just 1. So it looks like we just get 3 pi halves. Easy enough. So let's see if we can run through the center of mass problem for the same wire. What position is the average of all the mass at? Or what is the average of all the positions weighted by the mass, I would say. Don't want to do that. So let's think about this. There's some nice symmetry of this shape of this wire across the y equals x line. And that tells us, since the density is constant around this thing, it's also got that symmetry. The same on one half of the wire as it is on the other half. And because this thing is physically symmetric looking, it's geometrically, graphically speaking, symmetric across the y equals x line, we know the center of mass of this thing has to be along this y equals x line. I don't know, maybe it's around here. On average, where's most of the mass at? So that might be like our x bar, y bar. But since that is on the y equals x line, we know, just using symmetry here, the x and y coordinates of the center of mass have to be equal by the symmetry of this problem. The density is symmetric across the y equals x line. The actual curve, the region of integration, is graphically speaking symmetric across that line. It means the center of mass has to sit on that line. Nothing special about this side or this side. It better be right on the line. So that actually makes this pretty quick. If I want to find the center of mass, I just need to find one coordinate. One coordinate. Here it is. We already know the mass here is 3 pi halves kilograms, same as the units we used here. And x bar is going to be the line integral around this same curve. So all our setup here remains the same. Still pi halves to 2 pi. But now we're integrating, where is it? X times the density ds. Well, x on our curve equals cosine t. The density rho we already said is 1. And ds we saw is also 1 dt. That was this guy before. So we just put that x value in there. And now if we integrate, let's see what we get. Cosine integrated gives me sine. Evaluated from the bounds. That should disappear. At the top bound I get sine of 2 pi is 0, sine of sine of pi halves is 1, and so we get negative 1. Well, I need that divided by the mass, which we already found the mass was 3 pi halves. That divided by the mass. So it looks like at the end of the day I'm saying that the x coordinate of the center of mass is at the location negative 3 pi halves. Negative 2 pi thirds, sorry. Right? Okay. Let's see here. And since we're saying it's got to be equal to the other coordinate, we know y bar should be the same. So we should have these coordinates of our center of mass. Oops, I've switched this, right? This was 3 pi halves, the pi was with the 3. That sounds better. Let me switch this. Yeah. 3 pi halves, kilograms, negative 1 over 3 pi halves is negative 2 over 3 pi. That sounds better. And this is meters, units of length here in our domain, units of x and y. So y bar must be the same by the symmetry argument we made earlier. So we're saying we get roughly this. That's a little less than a third, a negative third in both directions. So maybe my point was pretty accurate looking. Right, this is a good point to make, that the center of mass does not have to actually sit on the object. In general, it probably doesn't for a wire. But this sort of follows our intuition, right? You might say, well, why is the center of mass down here and not up here? Well, there's sort of some mass missing from over here, so the center of mass migrates to where there's more mass, right? So if there's something missing from here, it's going to migrate towards the other side where there's a little bit more. It wants to be right in the middle of the average, or the middle of where all of the mass is. So this is our center of mass. Right, these aren't very hard problems, it's just more integral problems, and the work is really still just setting these things up. Setting up these iterated integrals, that's the work. Okay. Now the last thing I want to do in this video is see very briefly about these line integrals with respect to x, y, or z. The idea is pretty simple. So in the previous parts, if we had a function of two variables, we did these ds integrals along a contour C like the one I've drawn here. And the idea was that our step sizes that we took, the little ds, what it really came from, were little amounts of step size delta s from stepping from one point to another, from one t value plus a little bit to another along this curve. And so we sampled the function on each of those little pieces and multiplied by that size delta s of the step that we took, of the size of the interval we sampled from. So instead of multiplying by the step length of the arc length, this little delta s in our integral at each of those sample points, instead we're going to multiply by how much our x value changed when we took this step along the contour, or how much the y value changed when we took that step along the contour. And notice these can be negative values. And this delta s is always positive, but this, for example, in my picture here, the y value, if it started here, and then we went to this next point down the curve C, we go to a lesser y value, meaning delta y would be negative. It looks like integrating this curve with respect to y incorporates a negative dy value all along the integral. Right, so this is the basic idea. We're just replacing, instead of multiplying by ds, we're multiplying by the little amount of steps in the x direction, which can be negative, or the y direction, or the z direction. And how do we compute these? It's going to be extremely simple. Just remember that we said, let's go over here and remember we're referring to the usual setup. We have a contour C given by parameterization R of t from A to B. Let's again just think of these guys as having component functions x of t, y of t, z of t. Right. Well then, if we say we want to know what dx is, right, the rest is the same. We're just going to integrate from A to B, evaluate f at the parameterization, same as before. So plug in x of t, y of t, and z of t for your variables x, y, and z. And then if we want to know what dx is, it's easy. We have this expression. This is easy. The differential of x, usual way, is just the derivative of this side times the differential of its independent variable. It's just x prime of t dt. This is exactly what you do when you do an integral substitution. Like if I have an integral and I say u equals x squared, then du is just the derivative of this side times the differential of this side's independent variable. It's exactly what we've described here. X is some expression in t, so dx is the derivative of that expression times the differential of t. It's the exact same usual process we did over here. So instead of dx, all I have to put is x prime of t dt. Right now, notice we no longer have this magnitude r prime. That's nice. It's a little bit simpler. And same for all these. For the y integral, I like to write it again in this kind of vector notation because it doesn't imply that you have a function of 2 or 3 variables. It says just whatever space your curve C is in, plug those coordinates of x, y, and z on that parameterization, plug those into your function here. I suppose if we write down a z part, though, that does imply we're in 3D. But all these formulas are very simple. So, let's see these. And I should note before we get into some examples here that I should note something about the notation. Oops, don't want to do that. Well, I'll just put this picture back together later. I should mention something about notation up here. Notice, here we are. Notice if I took an integral of, let's just say it this way. If you see something written like p dx plus q dy plus r dz, where each of these p, q, and r are like our component functions in a field, they're functions of x, y, and z. It turns out this is just another way of writing This is just another way of writing the line integral along C of this function p with respect to x, plus the line integral along C of the function q with respect to y, plus the line integral along C of r of x, y, z dz. Right, so when you see this notation, it's just a compact way of expressing this sum of integrals. We'll see that this is actually more what we're concerned with. This is actually maybe the best reason to think of why we're studying these dx, dy, and dz line integrals. It's because we can express them together in this way, and we'll see there's a close relationship between these guys and the f.dr line integrals that we mentioned but haven't seen yet. So we're going to see where there's a connection here. We're going to see that connection between these dx, dy, z line integrals and these work integrals, f.dr work line integrals. So this is just a bit of notation for you. Let's move down here to this example now, if I can. Let me redraw my picture that I accidentally destroyed. Yeah, it's good enough. Okay, so let's evaluate this line integral over this curve C that starts at 0 at the origin, goes to 1, 1 along this curve, y equals x, and then goes back down to 0 along the cubic. Let's evaluate this thing. Notice this is exactly what we were talking about above. This is really just y dx integrated over C and x squared dy integrated over C. Just split it up, handle these separately. You will notice though this is a piecewise smooth curve, so we need to establish that this whole thing, let's call it C1 union with C2, union with C2, don't like my U there, but my eraser's not cooperating. So C1 and C2 will need to be parameterized separately. C2, there we go. So let's first parameterize C1, this straight line segment. That goes from the origin to 1, 1, so the equation of that line must be y equals x. So how are we going to do this for our parameterization of 1, 1? Let's just make it t, where t goes from 0 to 1. This is y as a function of x. Let x be your parameter. You know what y is in terms of that, right? Y is a function of that. Y is equal to that in this case. In that case, if I look at the magnitude of r prime of t, you can find, well, actually I don't need that. What we need is, well, let's put a pin in it. Let's save that. But for C2, how am I going to parameterize this? Well, it's the same deal here, right? We still have y equals negative x cubed. Y is a function of x. So let's do the similar thing here. But now notice it does matter our orientation. dx is negative if I go in this direction down my curve, the direction indicated by the arrows. dx is a positive value if I go the reverse of that. So I do need to start up here at 1, 1 and go down to 0, 0 somehow. How can I do that? Let's try just letting x be our parameter again. Then the y value that goes with that parameter, you might just think is t cubed. You might say, okay, that's from 0 to 1 in our x value, which is our t value. Does this work? If I plug this in, I am actually starting at the origin and going to 1, 1. That's no good. So instead, let's try this. Maybe we do negative t to negative t cubed, and we go from negative 1 to 0. If I start at negative 1, I get 1, 1. That's good. If I go up to a bigger t value of 0, I get the origin. So this is perfect. This is still satisfying the relationship that the y value is the x value cubed, but now we start and end at the correct place. And notice if I take magnitude of r prime, r2 prime, I get negative 1, negative Looks like negative 3t squared. I wish I hadn't done that. You can check my work on that. Yeah, negative 1, negative 3t squared. Right, the negative can come out of here. You're just differentiating negative 3t squared. Negative t cubed, which makes negative 3t squared. Also, then the magnitude of this guy, again, we don't need that. I keep pointing this at something we don't need. Yeah, we'll see why I even computed the derivative there. Maybe it's not clear yet. Right, I computed the derivative because now we actually have to set this up. We have to break up each of these c integrals into an integral over c1 plus an integral over c2. And now I can write down an iterated integral for each of these. On c1, I know my t is going to go from 0 to 1. And I know that the y value on c1 is t, right up here. And if I want dx, I just take, well, x is t, so dx is dt. Usual business there. That should be a 1. Okay. On c2 here, I know that it's going from, we did away with this, we're going with this parameterization. We know we're going from negative 1 to 0, and our y value now, our y value here is negative t cubed. dx, again, since x equals negative t, it's easy to get dx. It's negative dt. Negative flips that to a positive, t cubed dt. And moving on down, c1 again, back to c1, we know that again we're going from 0 to 1. The x squared is really just t squared. And we can get dy since y equals t, dy is dt. Finally, last little piece here, back to c2, back to this parameterization. We're going from negative 1 to 0. X squared is just negative t quantity squared, t squared. A dy is going to be, remember y is negative t cubed. Y is negative t cubed. So dy is negative 3t squared dt. My eraser's lagging behind my pen here. Right, so now this is easy. You could put some parts back together that are integrated from the same bounds. It wouldn't be too hard to do. For example, the 0 to 1 is both this integral and this integral. We can just write this as t plus t squared. Integrated from 0 to 1. Then negative 1 to 0 of, it looks like t cubed minus 3t to the 4th. You can group those back together. I'll let you finish this up. It's not hard from there. You have just two simple Calc 1 integrals. But I hope we see what this notation means and how to work out these dx, dy, and dz integrals. Okay, I just wanted to see one more. I appreciate you hanging in there. Maybe pause this and see if you can give it a shot. I just want to see one of these in R3 because I don't think we've seen one of those yet. The idea is exactly as before. Here it's nice. We're already given this parameterization. But notice this is in 3D. We have a function of 3 variables here because we're thinking of this curve as being in 3D. So this integral is going to equal, well, we're going from 0 to 2 pi. X is sine of t. Cosine y is just cosine of t. And ds, well, ds, remember, is magnitude r prime of t dt. So we need the magnitude of that derivative of that vector, r. The derivative is cosine 1 negative sine. I'll let you check my work, but I think the magnitude of that comes out to be square root of 2. So we're going to put a square root of 2 dt in the place of ds. This is pretty easy, I think. If we let u equal, I don't know, sine t, we see du is cosine t dt. Then our integral becomes the integral from when t is 0, sine of 0 is 0. But when t is 2 pi, well, sine of 2 pi is 0. Sine of 2 pi is 0. So no matter what we have in here, we're going from 0 to 0, right? This is 0. It doesn't matter what happens out here. So this is a line integral that cancels to 0. Notice ds is always positive, so it must be that we covered the same, we canceled out as much positive area as negative area with this sort of curtain we were considering. This is a little harder to consider that way because it's in 3D, so it's not just a curtain with the height given as the height above the xy plane given by the function. It's a little more complicated. There's a way to think about it, but we're getting as many negative contributions as we are positive contributions. It's all canceling out to 0 here. So that was a long video. I hope you took lots of breaks and tried some of these problems on your own before I went through them. We're going to finish up with these work integrals, the f.dr integrals, in the next video.